Welcome back, Focus Learner, to today's Explainer. It's August 26, 2026, and we've got an absolutely fascinating puzzle to unravel in the world of computational mechanics. Okay, let's dive right into this. We're looking at a truly groundbreaking paper by T. Gartner and colleagues over at Delft University of Technology and TNO. Their research zeroes in on a highly specific but absolutely critical engineering puzzle involving geometrically exact beams. You see, they've discovered and completely fixed a major mathematical glitch that happens when we try to geometrically scale up simulated materials in computer software. It's a brilliant piece of detective work in the realm of finite element modeling, and we are going to unpack exactly how they pulled it off.
So I want you to think about this for a second. How exactly do you simulate a crashing metal lattice? In the real world, things crash, they bend, and they break, right? To model these complex architectural lattices and ensure they're safe before they're ever physically built, engineers have to rely on some pretty heavy finite element mathematics. But there's a huge hidden catch here. What happens when you take a simulation that works perfectly for a tiny millimeter-wide strut and you try to scale it up to simulate a massive structural beam? Well, suddenly, the math just completely breaks down. The material literally stops acting the way it should in the software. And this exact problem is what this paper finally solves.
Here is our quick roadmap for today. First, the metamaterial revolution. Then, the math of beams. Third, the geometric scaling glitch. Fourth, fixing the hardening tensor. And finally, a size-agnostic future.
Section 1. The metamaterial revolution.
These metamaterials, and specifically architected metal lattices, are absolutely everywhere in our physical world. We see them in the weaving of chain-link fences, the production of everyday paperclips, advanced sports equipment design, and even in heavy-duty protective systems in military contexts. All of these lattice structures can basically be viewed as a massive collection of individual beams. And in all of these real-world applications, these metal lattices undergo massive, irreversible plastic deformation. Basically, they get completely crushed and permanently bent. Because of this, engineers desperately need incredibly accurate finite element computer models to predict their behavior and design them properly. Which naturally brings us to how we actually map that physical crashing and bending into a computer simulation.
Section 2. The math of beams.
To model these crashing structures computationally, scientists use frameworks like the SEMA, Reasoner, or nonlinear Timoshenko beam theories. But to understand exactly when a beam stops bouncing back elastically and permanently bends, we need something called the yield function. Think of this as a mathematical boundary in a six-dimensional space that determines exactly when a geometrically exact beam begins permanently deforming. We call that state plasticity. So the crucial point is that figuring out exactly when a beam permanently yields is incredibly complex. It's especially tricky when you're relying on sophisticated J2 plasticity models on the microscale, which assume the entire cross-section plastifies all at once rather than gradually.
When choosing how to mathematically model that permanent bending, we generally have two main behaviors. First, there's ideal plasticity. The beam yields, bends, and essentially stays bent. The force required to bend it remains totally constant after that initial yield. But real metals, they don't usually act like that. That brings us to the second behavior, kinematic hardening. Here, the material's yield surface actually shifts as it deforms, meaning the beam physically fights back. The force required to keep bending it goes up, creating a positive slope in the load displacement curve. Now, kinematic hardening is much closer to reality, but as we're about to see, it introduces some massive mathematical headaches when we try to scale it computationally.
To actually compute this bending in the finite element software, the system runs a constant, rapid loop known as an explicit return mapping algorithm. It uses a convex cutting plane method. First, it initializes the plastic strain and hardening variables. Second, it computes distresses and evaluates that yield function we just talked about. If the yield function boundary is crossed, it moves to step 3, computing the plastic flow update increment. And finally, it updates the plastic flow, strain, and internal hardening variables. This continuous computational loop is exactly how the simulation updates itself thousands of times as a physical load is applied. But what happens to that loop when we try to make our simulated beam larger or smaller in the software?
Section 3. The geometric scaling glitch. Well, Gartner and his team stumbled onto a severe problem when resizing these models. As they state right in their paper, while this framework provides scaling for the yield surface and ideal plasticity, scaling and hardening plasticity has not yet been explored.
I really want to emphasize this because it highlights a massive gap in the existing scientific literature. Up until this paper came out, no one had formally figured out exactly how these complex hardening tensors were supposed to scale geometrically when a simulated beam's size was changed.
To understand why this missing mathematical link is so catastrophic, think of a baking recipe. And this brilliantly illustrates the core issue: implicit versus explicit scaling. The basic elastic math in these models scales naturally. If you increase a beam's radius, the area implicitly increases in the math. It's just like scaling up the flour in a cake recipe based on the pan size. Simple, right? But the hardening tensor in these calculations is a fixed matrix. It wasn't naturally scaling at all. It's exactly like doubling the cake's geometric size but completely forgetting to explicitly double the baking powder. The entire recipe is ruined, and in our case, the whole simulation becomes mathematically unstable.
Let's look at the actual data the researchers pulled from their algorithm to see this failure in action. Pay special attention to the denominator in the plastic flow calculation. For ideal plasticity, it neatly scales by theta, which is our scale factor, to the power of -2. It aligns perfectly with the area inverse. But look at the hardening model. When that hardening tensor is left unscaled, that factor violently clashes at theta to the power of -6. The math is literally fighting itself inside the simulation, trying to mix a factor of -2 with a factor of -6 in the exact same flow equation. It's a total mess.
The physical result of this mathematical clash is pretty staggering. Depending purely on that scale factor, theta, the beam completely changes its simulated behavior. When theta is exactly 1, you get the expected baseline behavior. But when theta is less than 1, so you're simulating a very tiny beam, the unscaled hardening factor completely dominates. The beam falsely acts way too elastic, almost like bouncing rubber. Conversely, when theta is greater than 1 for a massive structural beam, the plasticity completely dominates. The hardening just vanishes, and the massive beam falsely acts like wet clay. The simulation was basically lying to the engineers. So now that we know exactly why the simulation breaks down, how do we fix it?
Section 4. Fixing the hardening tensor.
The root of the glitch lies right here in the kinematic hardening tensor, which is represented by a capital H. In formal terms, it's an invertible, symmetric, constant 6x6 matrix that dictates how the internal hardening variables relate to the hardening stresses. But simply put, it is the mathematical engine of the beam's physical resistance. The researchers realized that to stop the simulation from breaking and giving false readings, this specific tensor must be explicitly and geometrically scaled so that it perfectly matches the implicit scaling of the elastic stiffness tensor. Now, what's really interesting about this mathematical fix is their elegant solution, theta to the 4th power. By multiplying the bending moment components of the hardening tensor by the geometric scale factor to the 4th power, while carefully adjusting the other specific components like tension to theta squared, they perfectly rebalance the entire mathematical equation. They finally force the mathematical baking powder to scale perfectly alongside the flour, ensuring that the kinematic hardening stays proportional no matter the size of the beam.
And the proof is in the processing power. When looking at the algorithm's actual iterations from the study with the old unscaled hardening tensor, iteration 1 outright fails, resulting in inconsistent flow and a totally broken model. But with the newly explicitly scaled hardening tensor, the exact same return mapping algorithm successfully converges to a tiny tolerance of 0.001301 in just one single iteration. And most importantly, it does this consistently, regardless of whether the simulated beam is the size of a paperclip or a bridge strut. This mathematical fix is a real game changer for structural design.
Section 5. A size-agnostic future.
Gartner and his team have handed engineers a monumental victory here. Thanks to this newly scaled hardening tensor, we now have a completely size-agnostic formulation. We get consistent geometric scaling across all sizes. Engineers now have the ability to rapidly alter beam lengths and cross-sections in their software dynamically without any fear of breaking the simulation. This enables the safe, targeted design of highly complex metal metamaterials, entirely eliminating those spurious scale effects, like that weird rubber or wet clay behavior, even in severe strain scenarios. Engineers can finally, absolutely trust their software to tell them the truth about how these metal lattices will crash and bend in the real world.
Which brings us to our final thought for today. If we can now perfectly simulate material behavior at any scale, what unbreakable structures are we going to design next? From invincible sports gear to advanced, life-saving military defenses, the mathematically sound blueprints of tomorrow are officially cleared for drafting. Thank you, Focus Learner, for focusing in with me on this explainer. Keep questioning the math, and I'll catch you next time.